Okay, welcome to the series of lecture of Engineering Mathematics 2. So the first topic that I'm going to cover is the Laplace transformation. First concept, what is the meaning of transformation? The normal thing that we used to do in daily life is the addition. 2 plus 2 is 4. So it is nothing but transformation. This operator plus transform the 2 plus 2 into 4. Another thing is d by dx of sin x is equal to cos of x. So therefore, this derivative is a transformation. Similarly, we know that integration of x dx is x squared by 2 plus integral constant c. Again, this integration is also a transformation. So now, next question arises, what is Laplace transformation? So, in order to define Laplace transformation, we need to have some conditions. And in fact, to get a Laplace transformation, we should have some function. So, the basic definition of Laplace transformation. Let ft be any continuous function on open interval 0 to infinity. On open interval 0 to infinity. Then we use the notation for Laplace transformation as L of ft. It is nothing but Laplace of ft, where ft is any function. So we define this as, with the help of integral 0 to infinity e to the power minus st ft dt. Here s is the parameter. S is a parameter. This parameter s may be a real one or may be complex. Depends on the situation. This is not the complete definition right now. The integral that I have written on the right hand side, this integral, this should exist. Then only we can talk about the Laplace transform of the function. Another important thing, here we are integrating this as with respect to t, and therefore s will be a constant. So it will be entirely as a function of s. Now we will use this definition to get the Laplace transformation of certain functions. So consider the following situations. Suppose my ft function is e to the power at, where a is any constant. A is any constant. And I want to get the Laplace transformation of e to the power at. So by definition that we have studied, Laplace of e to the power at is a definite integral 0 to infinity e to the power minus st into e to the power at dt. Yes, it is like that. So we can write this as 0 to infinity e to the power minus s minus 8 times of at. Okay. So now this integral will be e to the power minus s minus a of t upon s minus a minus with minus sign from 0 to infinity. Exactly, it is like that. Now I can write this as minus sign outside upper limit, that is limit t approaches to a infinity, e to the power minus s minus a of t by s minus a minus e to the power minus s minus a of t by s minus a, and its limit is t approaches to 0. Now, as I had mentioned during the definition of Laplace transformation, that the Laplace transformation of the function exists if and only if this integral exists. It means this integral will exist provided this limit exists. This limit will exist. You know that if I give you a review, that limit x approaches to infinity of e to the power x, that moves to infinity. That can be just from the graph of exponential function also. It is like that. So it is the positive direction of plus infinity, so it moves towards infinity. Similarly, if the question is limit x approaches to infinity e to the power minus x, and please note that condition that x is strictly positive, then it moves towards 0. That can be also just from the graph. The graph of e to the power minus x is like that. Or somewhat it should be curved like that. It is asymptotic to x-axis, e to the power minus x. So that will tend to 0. Okay. So therefore, without loss of generality, what should I assume that? That the quantity s minus a should be a strictly positive, then only this limit exists. So therefore, it is equal to minus, then it will be 0 minus 1 upon s minus a, which is equal to 1 upon s minus a. The condition is s is bigger than a. This is the condition. So we have found the Laplace transformation of e to the power at, which is 1 upon s minus a, which is nothing but as a function of s, as I had told you in the definition of Laplace transformation. Okay, so let us move ahead. Okay, let us consider this situation also. Okay, so this board is a little bit creating problem, no issue, but we have to study. Okay, consider this situation. Situation is, I have to find the Laplace transformation of t to the power n. Please note that again, this n is either a positive integer, negative integer, or any real number rather than that. But this n can be any constant. N is any constant. Please note that it cannot be complex one. Okay. In order to get its Laplace transformation, I want to give you a review of gamma function. What is a gamma function? You must have studied that gamma of n is a definite integral 0 to infinity e to the power minus x, x to the power n minus 1 dx. This is review number 1. Review number 2, the property of gamma function, gamma n is n minus 1 into gamma n minus 1. Property number 3, gamma of 1 is 1. Property number 4, gamma of half is under root of pi. And please note that this gamma of only positive number is different. Only certain negative numbers are there for which we can talk about the gamma. Okay, so I will use these reviews to get the value of the Laplace transformation of t to the power n. So now, let us find the Laplace transformation of t to the power n. So let us consider this situation. So by definition, Laplace of t to the power n is a definite integral 0 to infinity e to the power minus st t to the power n dt. Okay, now I want to evaluate this integral. So let st is equal to v, so therefore dt is equal to 1 by s of dv, which is same as 0 to infinity e to the power minus v, and we can write this as t as v by s, which is nothing but v to the power n s to the power n plus 1 into dv. Why s to the power n plus 1? Because s to the power n from here and one more factor 1 by s. So because of that we are getting it as and, which is nothing but it is like that. What is this? It is the definition of gamma n plus 1. So which is nothing but gamma n plus 1 upon s to the power n plus 1. So we have found the desired result. So in this way we can get the Laplace transformation of some functions. Okay. So now I am giving you the list of the function and their Laplace transformation. Let us consider this situation. Now up to now what we have studied, Laplace of e to the power at is 1 by s minus number 1. Number 2, Laplace of t to the power n is gamma n plus 1 upon s to the power n plus 1. Okay, by same argument we can develop these formulas also. Laplace of sine at will be is a upon a square plus s square. Fourth one is Laplace of cos at is s upon a square plus s square. Okay, now these are the 4 formulas. On the basis of this we will develop some more formulas. Now let us do some application of these formulas. If I ask you what is Laplace transformation of one very basic question, so I can write this as Laplace of t to the power 0. So by definition it is nothing but gamma of 1 by s, and gamma of 1 is 1, so it is 1 by s. Okay. Similarly, if I ask you what is Laplace of e to the power 2t, we have studied that Laplace of e to the power 2t, in fact e to the power at as 1 upon s minus a. Here a is 2, so it is 1 upon s minus 2, like that. Similarly, if somebody asks you what is the Laplace transformation of sine t, so we know that the Laplace of sine at is a upon a square plus s square. So here a is 1, so therefore Laplace of sine t is 1 upon 1 plus s square. So these are some basic application of those formulas. Okay, one more question. Okay, not a question, properties. In fact, linearity property of Laplace transformation. Linearity property. What is the linearity property? That is Laplace of C1 f1 of t, that is f1 of t any function, plus minus, it can be either of the same, f of t is nothing but C1 L of f1 of t plus minus C2 L of f2 of t. It means this constant can be written outside the Laplace transformation sign. For example, Laplace of, suppose I have to write 2 sin t plus 3 cos 2t. Now 2 and 3 are constant, so that I can write L of sin t plus 3 L of cos 2t, which is equal to 2 times. So now what is the Laplace transformation of this? S square plus 3. What about this? It is s upon s square plus 4. So this is the final answer. So this way we can apply it. So the next one is how to find the Laplace transform of hyperbolic functions. Laplace transformation of hyperbolic functions. So now let us remove this particular part. Hyperbolic functions. You know that cos hyperbolic 80 is e to the power 80 plus e to the power minus 80 by 2. So therefore, Laplace of cos hyperbolic 80 is equal to 1 by 2 times of Laplace of, because this constant can be written outside the Laplace transformation sign, place plus Laplace of e to the power minus 80. So which is nothing but 1 by 2 into 1 upon s minus a plus 1 by 2 into 1 upon s plus a, which is nothing but 1 by 2 outside, and if we simplify it, it is simply s plus a plus s minus a upon s square minus a square, which is nothing but, if we simplify it, this will get cancelled with this. It is simply s upon s square minus a square, provided mod s is bigger than mod a. This condition should be hold, then only we can talk about the Laplace transformation of this cos hyperbolic 80. Similarly, we can find the Laplace transformation of sine hyperbolic 80. Now see that what is the Laplace transformation of sine hyperbolic 80. So for time being, I am removing this also. Sine hyperbolic 80 is defined like that: e to the power 80 minus e to the power minus 80 by 2. So if we use the same concept, it turns out to be Laplace of sine hyperbolic 80 will be simply a upon s square minus a square. You simply apply that property and you will get this value. Now, up to now, how many formulas we have studied? Now I am giving you the list of those formulas. So I can say that the tools of Laplace transformation. Tools means that is, these are the basic components. With the help of that, we can find the Laplace transform of any. Number one, we have studied Laplace of e to the power of 80 was 1 upon s minus a. Number two, similarly we can write for e to the power minus 80 also, simply replace this as s plus a. Similarly, studied t to the power n, which was, and fourth one is Laplace of sine 80, which is equal to a upon a square plus s square. And fifth one was Laplace of cos 80, which is equal to s upon s square plus a square. And sixth one was Laplace of cos hyperbolic 80, which is equal to s upon s square minus a square. And seventh one is Laplace of sine hyperbolic 80, which is equal to a upon s square minus a square. So please make sure that these 7 formulas should be in your mind. Then we can find the Laplace transform of several functions. So now let us consider few examples. Okay. Suppose the question is, find the Laplace transformation of sine under root of t. We don't know what is the Laplace transform is, that we want to find. We know that the sin x can be written as x minus x cubed by 3 factorial, x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial plus so on. So therefore, sine under root of t will be equal to root t minus t to the power 3 by 2 by 3 factorial plus t to the power 5 by 2 by 5 factorial minus so on. Now taking the Laplace transformation and using linearity property. What will be the Laplace of this? Laplace of this will be simply s to the power, in fact not, gamma 3 by 2 from s to the power 3 by 2 minus, it will be simply gamma 5 by 2 upon s to the power 5 by 2 3 factorial plus gamma 7 by 2 by s to the power 7 by 2 into 5 factorial. So you know that this can be written as gamma like that, and it can be written like that 3 by 2 into gamma 3 by 2 upon s to the power 5 by 2 3 factorial plus it can be written like that 5 by 2 into 3 by 2 into gamma 3 by 2 s to the power 7 by 2 into 5 factorial and so on. I can take this term as entirely as gamma 3 by 2 s to the power 3 by 2. Then what it will be? 1 minus, okay, it will be simply 1 by 4s, and then you will find that it is 1 by 4s square by 2 factorial. I can write this as 1 factorial. And next term, by the progression, I can say that 3 factorial is over, and it is nothing but gamma 3 by 2 s to the power 3 by 2, and what it will be? E to the power minus 1 by 4s. So that is the Laplace transformation of this function. So today's lecture we'll do the next part in the next video lecture. So we'll start from this point onward. So that's the end of today's video lecture.